The distribution function, f, for a plane shock wave has the same form for the Chapman-Enskog method and Grad's 13 moment approximation. It depends on the reduced molecular velocity, hydrodynamical velocity, temperature, viscous pressure tensor, and heat fluxes. To obtain the approximations, one must solve the Navier-Stokes Fourier equations in the case of the first-order Chapman-Enskog method, or what one may call Grad's 13 moment hydrodynamics. The former approximation has shock wave solutions for all Mach numbers, defined at the cold part of the shock, where the velocity is supersonic, but no shock wave solutions exist for Grad's 13 moment approximation for Mach numbers greater than 1.65. Therefore, Grad's approximation has limitations that do not appear for the Navier-Stokes Fourier equations that provide the reduced velocity, temperature, and fluxes for all Mach numbers. However, the comparison of the theory with experiments is not very good, and thus, the Navier-Stokes Fourier equations are in need of improvement. A problem arises for both approximations when trying to define the entropy in terms of Boltzmann's H function, since the natural logarithm of the distribution function is not defined due to the fact that, except for the equilibrium, two parts of the shock are given by the Rankine-Hugoniot jump conditions as the distribution function can be negative. Therefore, its natural logarithm is not defined. In the figure, the reduced distribution function and its dependence on the reduced peculiar velocity are shown at three different shock locations. It corresponds to a Mach number value of 1.55 in argon. Upflow is the cold part of the shock, where the flow is supersonic, while downflow is the hot equilibrium part of the shock, where the flow is subsonic. At the center of the shock wave, the reduced distribution function given by the Navier-Stokes Fourier equations has a region in which it is negative. Therefore, the natural logarithm of the distribution function is not defined. This implies that Boltzmann's H function is also not defined. Even for smaller Mach numbers, such as 1.55, the distribution function can be negative. For Grad's 13 moment approximations, there is not a perturbation parameter, like the Knudsen number, and we can consider the quadratic contributions in the perturbation. The figure shows the reduced entropy change as a function of the reduced distance for a shock wave with a Mach number value of 1.55. The red line is the result for the Navier-Stokes Fourier local equilibrium. The blue line is the local equilibrium reduced entropy change for Grad's approximations, and the green line provides the quadratic contributions in the perturbation for Grad's equations. Do you want to show your research progress to more scholars? Contribute an entry that will be linked to your paper on the encyclopedia platform, providing an opportunity for over 35,000 scholars to access and explore your research. Have you ever tried to show your latest research in a vivid way? Encyclopedia SciPlayer provides a service with which you can transfer your research to a live video format. Do you want to publish a new paper? Encyclopedia has an international, peer-reviewed, and open-access journal. Do you require a discount when you publish research in journals? Anyone who contributes to Encyclopedia can obtain vouchers for MDPI Journal's article processing charges. Encyclopedia aims to create an open-access knowledge-sharing platform for all scholars. To find more information, search for encyclopedia.pub.